Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. Today we're going to be talking about the NAND gate. We're going to introduce another gate. Up to this point we looked at AND, OR, and inverters, and we'll introduce the NAND. So the NAND is important for us because it's a universal gate, meaning that it can actually act like an inverter, like an AND gate, and like an OR gate. So all of the functions that we've been creating with our Boolean expressions using AOI can also be done with simply NAND. And this has some advantages in terms of reducing the number of chips that you need to use in a circuit, and also just having a uniform set of chips to use to create any circuit that you want to. So we're going to look at how the NAND behaves like a inverter, like a NAND gate, like a OR gate, and we're going to look how we can use the NAND and the procedure of using NANDs in a digital logic circuit to affect one of our truth tables, or a couple of our truth tables here. Okay, so let's get started. NAND gates. So we're going to start by just introducing what it is. So it's an AND gate followed by an inverter. So if you draw an AND gate like this, and then afterwards an inverter like that, what we get is, at this point we get X and Y, and then we invert the whole thing, X and Y with a bar over both of them. Okay, so this is the function of a NAND gate, and the symbol for a NAND gate is simply an AND gate with a negation bubble. So this is called a bubble, and so a negation bubble on the output there. And so in this case we have X and Y come in, and XY bar comes out. So this NAND gate does the same thing as an AND gate followed by an inverter. All right, so that's a NAND gate. What does the NAND gate truth table look like? So we're going to look at the AND gate and then the NAND gate. So the AND, if you remember, was only a 1 if all of the inputs were 1. And so the NAND gate is the inversion of the AND, so it's only a 0 when all of the inputs are 1, otherwise it's a 1. So that's what it looks like. Not that we're using that directly in any sense at this point, but I just wanted you to get an idea of what that truth table looks like, so that when we, if you ever are asked to, how its performance is, you'd be able to refer to this and understand that. All right, now let's take a look at how the NAND gate becomes an inverter, becomes a AND gate, or becomes an OR gate, how we can use it in that way. So NAND as inverter. So to create a NAND inverter, to substitute this, we simply connect the input together and put it into both inputs of the NAND gate. Sort of looks like a little mushroom there, if you will. And so this will give us an output that is X bar. So we're going to substitute this for an inverter, and that will give us what we're looking for. If you want to see the truth table of why that works, when X is 0 and Y is 0, we're dealing with this first row here, and that will give us an output of a 1. And so when X is 0, the output is 1, because both of these are X, right? And so when X comes in and it's 1, 1, if X is 1, we'd be in this last row and the output is 0. So when X is 0, the output's 1. When X is 1, the output's 0. So it's behaving like an inverter. Okay. So let's take a look at NAND as an AND gate. So in this case, we're going to be doing a double inversion. So if I have an AND gate, and then I invert the output, and then I invert the output again, we get back to the idea of this is just an AND gate. So it's the same thing. So inverting the output twice, this is a double inversion, does nothing to the output. So we get X and Y, and so this is XY, this is XY bar, and then this is back to XY. So that's functioning like an AND gate. So how does the NAND gate achieve that? Well, if you think about it, the NAND gate already has one inversion happening. So it's like this part right here, this first two. So I have XY, and then I have XY bar coming out. So we got to invert that one more time to make it an AND. And so now we'll use our new inverter configuration for the NAND gate, and then we end up with XY. So this is a NAND gate AND gate, if you will. Okay? So that's how we put together the AND gate. We have a NAND gate, and then the output of that gets split and put into both inputs of another NAND gate, and then it's an AND gate. Lastly, we have the NAND to OR gate. And this one, I'm going to do just a little more kind of, I guess, explanation, because I think it's worthwhile to look at this. So we can use De Morgan's to take this NAND, so this is XY with a bar over it, this is a NAND, and we can split or break the line and change the sign, and so we get this, X bar or Y bar, okay? And so from a schematic point of view, what this looks like is a NAND gate also can be thought of as an OR gate where the inputs are both inverted. So like that, okay? Another way to draw this is to take the bubbles and just attach them directly on the input of the OR gate. So we can draw this OR gate and put some bubbles, these are negation bubbles, on the input, and so this is the same thing. So this is essentially a NAND gate. So we're going to get here X bar or Y bar, which is equal to X and Y bar by De Morgan's. So these both are NAND gates. Okay, and it's helpful for us to look at this one to find our OR gate because we have an OR gate already built in there. So how would I make this a straight up OR gate? Well, it makes sense that we can double invert the input right here, and if we can do that, we'd have an OR gate. And so we're going to try to use our NAND gates to invert our input to our existing NAND gate, which looks like that, right? If we can do this, then we'd have an OR gate. And we know how to do this. So to make an inverter out of a NAND gate, it looks like that. So we have inverters out of both of our, made out of NAND gates. And then we'll just feed that into a NAND gate. And this is a NAND OR. Okay, let me just talk through that again really quickly. So by De Morgan's, we have XY with a bar over it, that's our NAND gate. And so we can change that to this version, this formation. X bar or Y bar. And so this NAND gate also can be drawn like this. And so this also can be drawn like the one below with taking these inverters and put them as negation bubbles on the input to the OR gate. And so this here is also a NAND gate. These are equivalent to each other, okay? And so instead of trying to make use this as our basis to make an OR gate, we're going to use this. So to make this into an OR, we have to invert our inputs X and Y first, and then that will cancel out these inversions because there'll be a double inversion, and we'll be left with the OR gate. So over here we invert the inputs to our NAND gate, and then that turns into an OR gate, and so then we're going to build that using the NAND gate configurations for inversion, and then a NAND gate replacement, not the OR version, but the AND version, and then this becomes our complete OR. So I know that's a little bit difficult to understand. Hopefully you can go through this a few times and make sense of it, but that's how we rationalize it. Now, if you're having a lot of trouble, really our focus here is creating these NAND digital logic circuits, so you could just remember and memorize that this is an OR gate and really not know the background behind it, and you'd still be able to be successful in doing problems that require this substitution. Okay. So let's put them to use. So we have our NAND as an inverter, just both inputs go into, the input goes into both inputs of the NAND gate, that's an inverter. Our NAND as an AND, we have a NAND gate, and then we have to get rid of the negation bubble, so we do an inversion on the output using the configuration from above. And then our NAND to OR, we need to invert both of the inputs to our NAND gate, so we use inverters on the inputs, and that's our OR gate. So let's do an example of how we can substitute in NANDs for a normal AOI circuit. So here's our example. We're going to do F is equal to the min terms 1, 2, 3, 4, 5, and 7. Okay, and so we have actually we don't need all of these here. So we don't need, oh, these are too big actually. Let me get a smaller set of these. So we don't need this guy, we need this guy, and we don't need this guy, we need this guy. It's a little bit clumsy dealing with this whiteboard, but we'll make do. Okay, that looks good. Hey, that didn't take too long at all. Nice. Okay, so let's go ahead and fill this in then with from our truth table, from our expression into our truth table. And so this is row 0, remember, so that's going to be a 0. But 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5 will have 1s on the outputs. And then row 7. So this is what the function looks like. So now we can take this and put it into our Carnot map. So we have X, Y, and Z. And remember, we break this up into groups of 4. So we got 0, 1, 1, 1, and the double 1 we have to skip, right? So we got 0, 1, skip, 1, 1. And then, since we don't have a double 1 going this way, we just go in a row here. So I have 1, 1, skip, 0, 1. So that is what our Carnot map looks like. And so if we do some boxing now, we have that, we have that, we have that. So we have the 4 in the middle, 2 on the bottom left, 2 on the upper right, and those are our boxes. So we can take that to write out an expression, and we're going to write it in our sum of products min-term kind of form here. So let's go from the top. We have a box of 4. That means that X changes, and we have Y changing. The only thing that's the same is Z is a 1, so this is Z. And then we have this box of 2. X is always 0, and Y is always 1, so X bar Y. And then we have this box of 2. X is always 1, and Y is always 0, so we have X, Y bar. So this is our AOI configuration, or this is just our Boolean expression, okay? And so now, what do we do from here? So let's write down some notes and procedure. So the first thing is we want to get the SOP from the K-map. So we get this expression in sum of products form from the K-map. That's step one. Step two is we're actually going to draw the AOI circuit like we know how to do. Okay? And then we're going to sub in for our NAND gates. And then lastly, we're going to simplify. So there's 4 steps here. So we get our normal expression, we draw the AOI circuit, and we're going to substitute in, and then we're going to simplify. All right, just so you know, we have some room here. I'm going to go ahead and move to a clean spot. There we go, that'll do. And so I'm going to repeat our expression here. F is Z or X bar Y or X Y bar. So let's draw the AOI circuit. And in the AOI circuit for sum of products, we have 3 sections. We have our inverter section, then we have our AND or product section, and then we have our OR. So I'm going to start over here on the OR side. So here's our OR. And then we have Z coming in by itself, so I'll just go ahead and do that. And then we have an AND gate here, and that's going to feed into the OR. And then we have an AND gate here, and that's going to feed into the OR like that. Okay, so Z goes straight in, and then we have X inverted going into one of the AND gates with Y. So there's Y, so then we have Y going into this AND gate right there. Then we have X non-inverted, so let's pull right here from X non-inverted, and then Y inverted going into the other one. So this is giving us our F. We have Z or X bar Y or X Y bar. And so that would be the AOI configuration for our circuit. Now we're going to substitute in for our AND, and so let's go ahead and get a different color for this. Sorry, our NANDs, right? And so let's go ahead and start with our OR gate. So in a NAND and OR gate, all the inputs will need to first be inverted. So we have 3 inputs. They're all going to be inverted with our NAND inverter. Okay. And those will feed into then a NAND gate. Okay, so this is our OR right here. Okay, and then we have our ANDs. And so the AND, remember, is a NAND gate followed by an inverter in NAND form. I have one here as well. So these are our ANDs right here. Okay, and Z doesn't need one, so we'll pull that back. So this is already to Z. But now we have these inverters as well. And so I have an inverter for X, and that's going to feed into this one. And then I have an inverter for Y, and that's going to feed into this one right here. So, and these are going to be tied together like that. Perfect. So we have X inverted going in there, and then X non-inverted is going to go into this one. Okay. And even though this crosses here, that's not a connection because there's not a dot there. So we put a dot when there's a connection just like that, just in case you didn't realize that. Okay. And so then we have Y inverted goes into that second gate, and then Y by itself goes into this first gate. All right. And I know it can get a little bit messy here, but that is the substitutions. So we substituted in our ANDs, we substituted in our ORs, and we substituted in our inversions right here. The next step is to simplify, and so I'm going to look for double inversions. And so as I go back from the output back in, I notice that this is a double inversion. And so we can get rid of that, because that does nothing to the signal from the beginning to the end. It inverts it once and then inverts it again. And there's another one right here. And because we are an SOP, this is common. We expect these double inversions to show up in between our AND gate and our OR gate. Since there is no AND gate on the Z line, that one stays, so that inverter will stay there. It won't be canceled out by the inversion coming from the AND gate. Okay? So those are the only two that get simplified, that get knocked out, and so we end up with something that looks like this beginning section. Those get knocked out, and then we have that end section. So let me redraw this down here. I know it's a little bit long to do, but that's okay. We have a little bit of time to take a look at this. We have now our two NAND gates that are ANDs, that represent the ANDs. We do have an inverter right here for the Z line, and that goes directly out to Z. And we still need our inverters for X, and then X goes non-inverted over here, and then we have Y. We need an inverter for Y. It goes right there, and then we need a non-inverted version of Y to go into the first gate. Okay, so we can see we have NAND gates for everything now, and we have a total of 1, 2, 3, 4, 5, 6 NAND gates to implement this. Okay, so we can put 4 of these NAND gates onto a chip, and so you need 2 chips to make this happen. Whereas over here in the AOI, you can put, you need 1 chip for the inverters, you need 1 chip for the AND gates, and you need 1 chip for the OR gates. So this actually takes 3 chips versus the NAND configuration, which takes 2. So we've simplified the circuit using all of the NAND gates in terms of what it would take to manufacture this. Okay, so that's it. That is our foray into using NANDs as a universal gate to build any of our Boolean expressions that come from a truth table. We can do it in this fashion. Just a quick review that we go through these steps. So we get the SOP form from the KMAP, like so. We draw the AOI circuit, like so. We do our substitutions, and then we simplify as much as we can. I'm Mike Stanzik. Thanks for watching. I hope you found value in this. As always, please like and subscribe, and I hope you have a great day.